Hello folks, today in this video we're going to talk about sound and interference. We're going to take a look at what sound is and how it works, and then talk about different properties that waves have, including interference. Let's get started. So first off, let's talk about what sound actually is. Sound, as we've talked about before, is a type of longitudinal wave. That means that the particle motion is parallel with the direction of wave travel. And we observe it, of course, by detecting vibrations in our ear. So it's just a particular type of wave, but this kind of wave comes up quite often. One thing to note, you might have heard of this before, the speed of sound, right? Breaking the sound barrier. The speed of sound is a constant, so that's why it's a useful thing to talk about at a given temperature and pressure. And here's one that I'll put on your reference sheet for you. The speed of sound in air at STP, standard temperature and pressure, is 331 meters per second, which sounds fast, right? 331 meters per second. It's like 3 football fields in a single second is a lot, but it's not that fast. Definitely not as fast as the speed, of course, of light. We've talked about the speed of light before, and the speed of light is 3 times 10 to the 8th meters per second, which is 5 orders of magnitude greater, or 6 orders of magnitude greater. That is much, much, much faster. This is why, for example, if you're watching a marching band has to watch a conductor rather than actually listen to the sounds they're hearing, because the conductor, their hands moving, is light being transmitted much faster than sound. You can actually get off in terms of tempo between two different sides of a marching band because of that slow speed of sound. So speed of sound is a constant in a given medium. The loudness then of a sound is related to the amplitude. So remember that amplitude of any particular wave is related to that wave's energy, and therefore the loudness of the sound is how much energy that wave is transmitting to us then. The pitch of a sound, pitch is how high or how low the sound of something is, and that is related to the frequency of that wave. So the higher the pitch, the higher the frequency. And because of our wave equation, V equals F times wavelength, we would know that it has a higher frequency, it would have a shorter wavelength. It has to have a shorter wavelength because the speed has to stay the same, because the speed of sound is a constant. So that's a little bit kind of basics about sound and how it works here. I want to talk a bit about that sound barrier thing. You might have heard of that before. It's a really common thing to hear in science fiction or science movies. The sound barrier, it's the idea behind it. It's not really a barrier so much as that it's a region of intense aerodynamic drag encountered as an aircraft approaches the speed of sound. So what all it is that as an aircraft or any type of flying object gets faster and faster and faster, it approaches a period where the stresses on all of the different mechanical parts are really large because they're getting very close to that speed of sound. And actually, once they pass through it, you enter a region where the aerodynamics changes, and it's actually a little easier to travel through after you've gotten to that place there. You might have heard of a Mach number before. For example, something's going Mach 2 or something like that. It's just a speed of an aircraft going as a multiple of the speed of sound. So if somebody says Mach 2, or you hear that an aircraft is going Mach 2, it's just going twice the speed of sound. I put down some common Mach numbers for different aircraft. A Boeing 747, one of the most common aircraft that you could be flying on until Airbus takes them over, is just under the speed of sound if it's going as fast as it possibly could, 0.92 in terms of Mach numbers. An F-35, which is one of the newest fighter aircraft the United States employs, can go about 1.6. An intercontinental ballistic missile, an ICBM, these are those things that you see in movies that are carrying nuclear warheads from one place to another. Those go Mach 23. That's why they're very hard to shoot down, because they go 23 times the speed of sound. And then the space shuttle tops it all and actually could go at top of Mach 25 at its fastest. So those are some cool numbers to kind of relate to when it comes to sound and its speed. I got a few questions for you here, some speed of sound examples. This first one asks, the sound wave produced by a trumpet has a frequency of 440 hertz. What is the distance between successive compressions of this sound wave as it travels through air at STP? So one thing they've done is they've been mean, and they've said distance between successive compressions. What does that mean? Well, if you think about a wave, here I'm going to draw kind of a longitudinal wave. So remember that it has parts where it's denser and parts where it's less dense. So if these are your compressions, the distance between those, of course, is the wavelength of that wave. So all it's asking for here is the wavelength given the frequency. So you might think, okay, I know an equation for wavelength and frequency. I know V equals F times lambda, but they didn't give me the V. But notice they told you that it's at STP. And remember, the speed of sound at STP is 331 meters per second. So that's going to equal the frequency, 440 hertz, times the wavelength. And you solve that out using your calculator for that wavelength. And I get a wavelength of 0.75 meters as my wavelength there. Number two, not number one, sorry. At an outdoor physics demo, a delay of 0.5 seconds was observed between the time sound waves left a loudspeaker and the time these sound waves reached a student through the air. If the speaker's at STP, how far was the student from the speaker? Well, it's not like a wavelength question because it is asking me for a distance. How far, but it's not a question about wavelength. This actually goes back to something you probably learned about in Physics 1, talking about V as distance divided by time. We know the speed of the sound if it's in air at STP, 331 meters per second. I can relate that to the distance it's going to travel in 0.5 seconds. So don't forget, waves do travel a distance. They have a wavelength, but they also go a physical distance. And so that's what it's asking for here. So we'll just use this 331 times our 0.5 seconds, gives me a distance of 166 meters when I round a bit there. Okay, so that's some basics for speed of sound practice. I next want to talk about the speed of sound in other materials. Well, I have said that it's constant in air, but what is it when you go to different things? Well, the speed of sound can vary quite wildly. I'm actually kind of blocking a bit of it here with my camera, but you can see there are some very fast speed of sounds and there's some, fairly slow. Actually, it looks like air. Air is one of the lowest speeds of sound that you actually could have, at least on this list here. So what affects the speed of sound? Well, there's two things we're going to talk about. We're going to talk about it qualitatively, and we're going to talk about it quantitatively. The qualitative way is kind of summarized by this table. This is not a table you need to have memorized, but you should know the general trend that's happening here. I want you to see first between gases, liquids, and solids. In general, as your phase goes from more spread out to less spread out, from gases to liquids to solids, the speed of sound increases. So you get an increasing speed of sound. But there's another effect going on here as well that you might want to try to see. If you think about it, the gases are probably the easiest way to see this. Hydrogen is by far the lightest gas you could have. Air is a heavier gas, at least in this particular list here. Helium, nitrogen, oxygen would all be a bit less. So you might notice that as the gas is getting denser, the speed is actually going down. That's an odd effect, but in general, the higher the density, the lower the speed of sound in a particular phase of matter. But then once you go up to liquids, obviously liquids are more dense than gases, but they are faster in a liquid. And that has to do with the way that the particles are arranged in the different phases of matter and not to do exactly with the density there, more with the compressibility factor there. But once you go to liquids, again, you see the same thing where the denser the liquid, the faster it's going to go. The slower it's going to go. And then same thing in the solids, where very dense things like lead will actually have a fairly low speed of sound, where, things that are much, much less dense, diamonds aren't very dense at all, have a very high speed of sound there. Now, if we want to look at this quantitatively, there are two equations that we can use. We've got the speed of sound in a string. This is a very particular equation, and it is the square root of the tension in the string divided by u, or the Greek letter mu, where mu is the linear density. Linear density, I didn't put the equation on here, I just kind of put it there. It's just mass divided by distance. And this kind of captures that idea that the greater the density is, the lower the speed. If you have a string that it's a solid, obviously, but the denser it's going to be, the larger that mu is going to be, and then consequently, the slower the sound. And the tension, of course, measured in newtons, that's a force. It's just how much force that string has. If you've ever played a stringed instrument, you might know that you tighten those strings to get it to be a higher pitch, like a guitar. So the more you tighten it, the greater the tension, the faster the sound, the higher the pitch. Yeah, if you lower it, and then it will vice versa. The other equation we have is very similar. It is just, in general, the speed in any material. So this is specifically for a string. This is for any material, and it's the square root of B, the bulk modulus. That is to deal with the incompressibility of it. That's kind of capturing that gas, liquid, and solid idea there. Incompressibility, the idea behind that is a gas is very compressible. You can easily compress a gas. You cannot compress a liquid quite as well. If you've ever tried to squeeze a water bottle completely filled with water, it's very hard to do. And a solid is obviously like nearly impossible to compress. It takes a very high force to get a solid to get any smaller. So that's how it explains the effect from gases to liquids to solids. But then on the bottom is density, just like we saw before there. So that's another way you could calculate the speed of sound given things for a material. Next, I want to try a kind of a different kind of question here. This is about calculating speed of sound in a different material here. It says a research ship uses sonar to send a 1.1 times 10, that should say times 10 to the third there, sorry about that, hertz sound wave down to the ocean floor. The reflected sound wave from the flat ocean bottom, 324 meters below the ship, is detected 0.425 seconds after it was sent from the ship. We got 3 questions. Go ahead if you want, pause the video, give them a try, come on back, and I'll walk you through how to do these ones. Okay, so to calculate the speed of the sound wave, I'm going to use that V equals D over T because I don't know what the speed of sound is in water. I'm not going to give you those ones on that last slide there. So we're going to have to calculate this out here, actually. To do that, I'm going to use distance divided by time because I know the frequency, but I don't know the wavelength. So to get my distance, it's tempting to just use the 324. But think about what's happening here, right? If I have my little boat, sorry for my terrible picture of a boat, and it's sending down a signal to the ocean floor, that signal also has to get back to the ship before it can actually detect that signal there. So this distance is going to be 2 times 324 meters. And then the time will be 0.425 seconds. So don't get trapped by that. That was kind of a trick question there with the way that sonar works, which is a pretty cool thing. You should look it up. But I got a speed of sound of 1,525 meters per second. And just out of curiosity, that looks like it's pretty close actually to what it was here. It must be just a little warmer than that 25 degrees Celsius. And then calculate the wavelength of the sound wave in the water. Now I can use that equation, V equals F times lambda there. I know the speed is 1525 meters per second. That's going to equal the frequency, which was 1.18, times 10 to the third hertz, times lambda, which is my wavelength. Divide that by 1.18 times 10 to the third, and I get a frequency, or a wavelength, of 1.29 meters. Last question it asked me to do is just determine the period of it. Remember that period is just the inverse of the frequency. Sorry about that there, guys. And since I know the frequency is 1.18 times 10 to the third hertz, just take the inverse of that number there. So 1.18 times 10 to the third, take the inverse of that answer, and I get, I'll put it over here because I'm running out of room, 8.47 times 10 to the minus fourth. And it would be seconds. So quite a small number, which makes sense because that is very high frequency here. Okay, moving on there. Now we got to take a look at some wave phenomena, things that waves can do. In general, there are a ton of things that waves can do. We're going to talk about some of these tonight. Actually, one of them we've already talked about, which is resonance, which is the vibration of one object caused by the vibration in another object, that forced vibration idea there, if it's close to its fundamental frequency. But we're going to take a look at these ones tonight. We're actually going to save this bottom one there until we talk about light specifically. Obviously, all kind of waves can do reflection and refraction, but we're going to save it for light because it really makes a lot of sense when talking about that there. So we're going to talk about the other ones in no particular order, but Doppler effect is going to be first. So the Doppler effect, you might know from the fantastic show that got a little bad at the end, Big Bang Theory, where Sheldon dressed up as the Doppler effect. The Doppler effect is an observed shift in the frequency of a wave due to the relative motion. I want to emphasize observed shift. It's not that the frequency actually changes, it's just that it appears to change for you as the observer because you are moving. In general, if you are moving toward an object, so you can see this biker here is moving toward the source of a wave, those waves are going to kind of get closer, appear to get closer to you because of that relative motion. So they'll kind of bunch up. If they're bunched up, the frequency appears to be higher. And so we would cause that to be, or call that to be blue shifted. The idea being that a blue shifted wave is more toward the higher frequency blue side of light, the electromagnetic spectrum there. So if you go towards something, the frequency goes up. If you're going away from something, the argument is the same. As you're going away, those waves will kind of seem to spread out. They don't get to you quite as fast. And so the frequency appears to be lower. We call that red shifted. And you might have heard that when it comes to galaxies and stars and stuff, where we can tell that galaxies are moving away from us when their light looks redder and towards us when their light looks bluer. So that is the Doppler effect. There is actually a way to calculate the amount of the Doppler effect. It is using this crazy equation. Now, I've typed it out here because it's on your reference table like that. However, I think it's much easier to see it even with my terrible handwriting. So we'll write it like this, that it's F prime, which is the new frequency, the observed one that you're going to hear, is equal to the old frequency, F, times, on the top of this fraction, V plus or minus, V with a little d at the bottom, and then V minus or plus, V with an S at the bottom, where Vd is the speed of the detector and Vs is the speed of the source. Okay, we got to talk about this equation and how to use it because it's kind of tricky. The idea being that plus and minus changes depending on what situation you're in. So there's 4 scenarios that you could see yourself in. Let's imagine that you are running away from a train. Here is a beautiful train. Look at that. Awesome. Nice train. And it is running toward you or traveling toward you at 10 meters per second. And you're going to try to run away from it at, let's say, 5 meters per second. So it is coming away from you or toward you, but you're going away from it. The idea behind this equation here is that we're going to set it up such that the top of the fraction and the bottom of the fraction both work how they should based on the Doppler effect. So what we're going to do is consider first the top. It's going to be the speed of the wave of, this top V is the speed of sound. So this is going to be your normal speed of sound for whatever material you're in. For example, if you're in air, 331 meters per second at STP. And then the plus or minus depends on what is happening to the detector. You're going to be the detector because we're hearing, of course, the train whistle, hearing at us, and we are moving away from the train. What would that do to the frequency? Well, if we're moving away from the train, we should hear the frequency go down. So on the top here, I need to use a minus 5 meters per second because I would be hearing it go down based on my motion and my motion only. Then on the bottom of this fraction, we put a V there. And then we're going to consider, now we've done me. Now we're going to do the train. The train is moving toward me from its perspective. It is traveling toward me. And so that would tend to increase the frequency, right? And so because of that, I need the bottom of the fraction to increase the frequency. Here's where it takes a little bit of a math leap. On the bottom of a fraction, to make something go bigger, I would need to subtract off the 10 meters per second, because in general, a smaller thing in the bottom will make this go up. So I'm going to use a minus and minus here if I'm going away from the train, but the train is going toward me. Okay, I hope that's making some sense. Let's try the other scenarios because it might start kind of clicking for you if you see the other way these could work. So same situation. Train is still moving toward me, but now I'm going to go and turn around and travel toward the train. So same equation. But the idea now is if I'm going based on the detector, which is me, I'm now traveling toward the train. In my point of view, I am traveling toward the train at 5. So I, from my perspective, would hear the sound go up. And so I am going to be adding my 5 on the top there. That's what makes this situation different than this situation. On the bottom, though, the train's the same. The train is still going toward me. And so that means there's a minus on the bottom. This is the situation with the highest observed frequency because I'm going toward the train and the train is going toward me. Okay, let's completely flip things. What if now I'm chasing a train? So train is now turned around. It's going away from me at 10 meters per second. And I'm actually running away from the train too. So we're going to do this scenario where train's going that way and I'm going that way. Observed frequency would be, for me, the detector, I'm still running away from the train. So it's still a minus 5 meters per second on the top. But now in the train situation, because it's the source of this sound, it's going away from me. So I need the bottom to also make this frequency smaller. So I'm going to be adding 10 meters per second on the bottom there. So hopefully you're kind of seeing the idea behind this now, how this plus and minus changes things. Hopefully you might be able to do the last scenario on your own, but just to show it to you, the way it would work, here's my train, 10 meters per second. Here is me still chasing the train at 5 meters per second. And so it's going to be F prime equals F times on the top V. I'm going toward the train, so plus 5 meters per second, but the train's going away from me, so V equals V plus 10 meters per second. Okay, that's how you calculate the Doppler effect. Now we got less math, just talking about some other ways or other things that waves can do. So we got diffraction. Diffraction is the bending of light waves around obstacles or the spreading of waves as they pass through an opening. You might have seen this before if you ever watched ripples in a pond going through some type of barrier or going around a rock or something. In general, waves, when they encounter some type of barrier, they tend to spread out once they get to that barrier there. In general, the smaller the opening, the larger the diffraction. If there is a smaller opening here that you're trying to fit these waves through, they need to spread out more once they actually get to that barrier, and then you're going to get more diffraction as they go through that. And we're going to take a look at diffraction later in the course as well. So this won't be the only time that you see diffraction there. Then we've got interference, a very interesting and important concept. Interference, when two waves meet at the same point, they what we call interfere, depending on their relative amplitudes. There's a law about this called the law of superposition. Superposition tells us that at any given point, the total amplitude of that point is the sum of all the individual amplitudes of the waves. What does that mean? Well, waves are interesting. When waves interact, they don't actually destroy each other. They can actually just pass right through. So if wave A and wave B are coming together, they're going to meet somewhere in the middle. And this law tells us that when they do, their two heights, if this is the height of A and that is the height of B, will add up to produce a total amplitude that is the sum of both of those. That is wave interference. Interference always sounds like it's negative, but it actually can interfere both to make a bigger total wave or less of a total wave. And then the key other point is that once they've interfered with each other, they can just keep passing through each other and they'll just keep going their respective waves or ways. So those waves continue on going through the next thing there. So I kind of alluded to it that there are two different kinds of interference. There's constructive and destructive. Constructive interference occurs when you have two waves of similar or the same frequency and amplitude. When they line up, those two amplitudes line up in the same direction, or we would say these waves are in phase with each other. They're in the same phase angle. And so when they add up, they're going to combine together to create a total wave that is bigger than either of the other two waves. The other thing you can have happen is destructive interference. This is when they have the same amplitude and frequency, but they line up in opposite directions from each other. They're lined up out of phase. These ones are perfectly out of phase. That is, they're exactly pi phase angle away from each other. Of course, they could be a different amount, and there still would be some interference. This is just the maximal amount of constructive interference. And when they would combine, these two waves would have absolutely no amplitude whatsoever. They would completely cancel out because this wave is going up just as much as this wave is going down. And that's a very interesting effect that can actually happen. This is how noise suppression or noise canceling headphones actually work, where if they detect a wave coming in, they play a wave of the opposite amplitude to get them to cancel out there. Once, of course, they've passed past each other, though, they will continue on undisturbed. So that's wave interference. One really interesting way that it comes up is in the idea of a standing wave. What a standing wave is when you have, let's say, two people holding a piece of string and they start vibrating that string back and forth. If you have a particular frequency that you do that vibration at, it'll create waves of the same frequency and amplitude traveling in opposite directions. When they meet, they will interfere according to this principle. And what will happen is you get a wave that appears to be stationary, hence the name a standing wave. So this standing wave has certain properties. First, there are points where it seems to have a maximum amplitude, and points where there is no amplitude whatsoever. The points where there's no amplitude, we call that a node, where I put a little n here. So there's no displacement, it appears to be, due to the destructive interference between the waves. It appears to be still. You also get antinodes here. This is one antinode, even though it looks like there's one at the top and the bottom. This is just one antinode, and that's a point of the largest displacement due to the maximum constructive interference, and that's where it has the maximum amplitude. Now, where are standing waves important? Standing waves are important in music. Anytime you play a musical instrument, you are going to be creating a standing wave based on the fundamental frequency of that particular instrument. So if you pluck a guitar string, you will get a standing wave that looks kind of like this one here. Sorry, that kind of looks like I've screwed up the diagram there. So to create a standing wave on a string, you have to have a node at both ends. And you might know that you can play multiple notes on a music instrument, even in the same position. These are called harmonics there. You can hear a lower note and then a higher note can be played with the same string in the same position. In general, those harmonics make sort of a series based on the different standing waves that you can get. And there's an infinite number of these. This is a picture of what they look like. And here's how we could calculate the wavelength of those standing waves based on the length of the string, and then n, where n is which harmonic you're talking about. This here we would say is the first harmonic, the second, the third, so on and so forth. Similarly, you can get the same thing with pipes and tubes. And if you've played a woodwind or brass instrument, this is probably way more familiar. If you've ever played a trumpet, you know that there's only 3 keys in the thing, but you can play a lot more notes than just 3 because you can lower or raise the pitch of that note by playing a different harmonic. Now, the equations are a little different for pipes. In general, if the pipe is open on both ends, it works very similar to a string. A string had to have a node on both ends, but this just has to have an antinode on both ends. So you get a first harmonic, a second harmonic, and a third harmonic. So the equation works the same. But for a pipe with one open end and one closed end, this is like an organ pipe, these are very different. You have a node and then an antinode, and so you only get half as many harmonics in the same amount of frequency space. And so you end up needing to take and divide this n, or this equation, by odd numbers of n, not any number of n. But I'll include those formulas for you on your reference sheet so that you know which one to use in which situation. Okay, folks, that's been a lot about lots of different waves. Thank you guys so much for watching. Have a great rest of your day.